Good afternoon, all. Welcome to the Samvaad talk series. Today is the last talk on the cybersecurity theme by Professor Roland Haas, and the title of the talk is Trends and Challenges in Automotive Cybersecurity. Today's session will be chaired by Professor Srinivas Vivek, who has obtained his B.Tech in Information Technology from National Institute of Technology, Surat Kal, India in 2008, followed by his MSc Engineering at the Indian Institute of Science, Bangalore. He completed his PhD from the University of Luxembourg in 2015, where he was affiliated to the Laboratory of Algorithmics, Cryptology and Security in the Computer Science and Communications Research Unit. He was a postdoctoral research associate in the cryptology group of the Department of Computer Science at the University of Bristol between 2015 and 2017. He joined IIIT Bangalore as an assistant professor in January 2018, and his main research interests are in the design, analysis, and implementation of side channel countermeasures and homomorphic encryption schemes. So over to you, Professor Vivek.
Yeah, thank you, Professor Amita Mishra, for the kind introduction and giving me an opportunity to chair this session. It's a great pleasure to welcome Professor Roland Haas. So Professor Haas is currently a professor at our institute. He joined full-time in April 2021 after a 15 years association with the institute as an adjunct and honorary faculty member. He has about 25 years of professional experience in research, senior techno-managerial, business innovation, and business development assignments in Germany, India, USA, Japan, and Israel. Dr. Haas has broad experience in automotive R&D, aerospace R&D, systems engineering, software and IT services, consulting, and strategy. So between 1993 and 2006, he worked with the Daimler Group, heading the Daimler India R&D Center in Bangalore, now called MBRDI, between 2001 and 2006. In 2007, Professor Haas founded the company QSO Technologies and worked with clients in Europe, US, and East Asia. Professor Haas has also co-authored several books, the most recent one being a textbook on automotive connectivity and cybersecurity published by Springer. Currently, he's teaching course on automotive security, and I'm one of the elderly students in his class. Dr. Haas was also an adjunct faculty member at the Indian Institute of Science and has done teaching and research in cybersecurity, automotive, electronics, car IT, software technologies, autonomous systems, management information systems, and virtual product creation. He is an alumnus of the German National Academic Foundation and the Mercedes-Benz Scholarship Foundation. Dr. Haas has studied computer science, mathematics, and electrical engineering at the University of Karlsruhe, now Karlsruhe Institute of Technology, KIT, and the Technical University of Gloucester. So Professor Haas will be speaking today on trends and challenges in automotive cybersecurity. So let's once again welcome Professor Haas. I'm eager to listen to this important topic in cybersecurity, also an exciting topic. Over to you, Professor Haas.
Thank you very much, Professor Srinivas Vivek. Thank you very much for the kind introduction. Thank you for the team organizing this session. I will talk today about automotive cybersecurity, which is embedded in the larger cybersecurity issues of critical infrastructures. Let me start with a quick overview of what I would like to talk about. I will start with automotive megatrends and the digital transformation of the automotive industry. Because when we look at cybersecurity, we need to see where the industry is heading and what trends are relevant for cybersecurity. So we will look at that, what it means for cybersecurity, what those trends actually mean and what implications they have. Then I will show you some information on the evolution of electronic and electrical architecture and software in cars. And we touch upon car hacking and automotive cybersecurity. We then look at a very fundamental system, the cybersecurity management system that orchestrates all the cybersecurity activities in the company. We look at hardening of the system, defense in depth approach, and we will touch upon the regulatory framework, the WP.29 and the ISO 21434. These give a standard and a predictable standard now for the automotive industry, what they have to do in order to cyber secure the products. And finally, we will look at cyber threats at two segments. One is battery electric vehicles, the other one is ADAS and autonomous vehicles. Here we can just look at the very vast topic, but it should motivate what issues can come up, especially with respect to those two megatrends. And finally, outlook and some research areas. What topics are very relevant for research I would like to talk about and summarize my talk. So that's for the next 45 to 55, 60 minutes, the program to show you. Now let's start with the megatrends. The automotive industry today is changing fast and maybe faster than ever before. And what are the drivers of this digital transformation process? One of the drivers is that what you could call the case connected, autonomous, shared mobility and electric cars. And some are using different permutations of that. What it actually means, the car is connected, it sends its data to the cloud and back. We will have autonomous driving in different steps towards autonomous driving. Mobility is shared. Car is not just owned, but shared. We know those mega trends like Uber or Ola that actually have, kind of revolutionized the way we see mobility today. And then the mega trend electric cars. We are majorly shifting towards electromobility, and we will look at that in more detail. But apart from that, there are some other megatrends that often are a little bit, in the second position or overlooked. But these megatrends are also very important from the cybersecurity perspective. There is an increased share of software. Experts estimate actually up to 500 million lines of code in a high-end autonomous battery electric car. That would mean that the car in that setup becomes the most complex and elaborate software system that has been designed so far. We also see high performance computing platforms that actually outperform the most performing or highest speed desktop systems available today. And some call it vehicle computers. So large platforms in the car for high speed processing. We will have a full cloud integration. Vehicle functions not running only on the car, but they will run in the cloud. How does it interact? What are the repercussions of that? And we will have a disrupted, and we see the consequences right now, a disrupted supply chain. Actually, the chip shortage is so severe that some of the automotive OEMs had to stop production. They're just waiting for the ships to be delivered. 50% of the world chip market is dominated by just one manufacturer, TSMC in Taiwan. And startups drive innovation. We will see that this also has a consequence for cybersecurity. So OEMs have, made startups as part of the ecosystem, and they're relying on their innovation to integrate that. And as we say that the borderline between OEMs and tiers becomes blurred with a lot of consequences in terms of roles and responsibilities. An example of that is Bosch offers now a full range rolling electric chassis where anybody can build a car on top, and VW sells its platform to other OEMs who can build their cars on the platform, which you see in the right button there. Now, auto tech startups are driving information. Just a look at such landscapes. They are just mind-boggling, and you can look at it in Asia as well in US. This is from Europe. You see what automotive tech startups are actually driving innovations in different fields: autonomous vehicles, mobility service, e-mobility, battery technologies, parking, smart cities, hardware, but also services like finance, insurance, and of course, this large domain of connected vehicles and vehicle-to-X, vehicle-to-everything communication. Let's look at the example how the industry is changing, and we will look at the example of Volkswagen. Now, the past Volkswagen plant here in Wolfsburg was capable of doing 6,000 internal combustion engines a day. classical industry, manufacturing optimized, output of maximum 6,000 cars a day. And they produce cars like this one, the Bugatti Veyron Grand Vitesse. This is a picture from Wolfsburg. These cars, actually, their car owners are so attached to them, they take them over for any refurbishment or checkup. But such a car, had specifications that's just mind-boggling. 1,500 horsepower, 430 kilometers an hour, a powertrain with 16 cylinders, and from 0 to 400 and back to 0 in just 50 seconds. That was the old days. People were impressed by this. But today with e-mobility, those features are not that much impressive, because e-mobility, as you know, from any RPM, the torque is there and you go in an extremely, nice way. The cars are amazing if you look at that. But now, example Volkswagen, what it is today. Today and the future. There will be an all-electric product line. No ICE car anymore, no combustion engine more, from the different product brands from Volkswagen. This is the Volkswagen brand itself, but Porsche and Audi have all their e-cars. In about 10 years from now, there will be no ICE cars anymore. The systems will be fully connected. There is a cloud, and VW works together with Microsoft or AWS, Amazon, to integrate those cloud architectures. So all the data from the car can be integrated in the VW cloud. But what might be not so well known is the energy market. While producing electric cars, VW also enters the energy market. So they look into charging, they look into virtual grids, they look into the ways they can actually provide services around electricity. And the brand they do that is called Elli. Shared mobility, we talked about that. Shared mobility for Volkswagen has meant that they bought back Europcar, a car rental company that they had spun off some time ago. They bought it back. There's experimenting with a lot of shared mobility concept here. One is shown Moya, that actually allows you to hop into a car, will be electric driven, and provides mobility service in cities like Hamburg or Hanover. And then this transformation also is a massive transformation towards software. So today, 4,000 software engineers are part of a new entity called CARIAT, carsoftware.org before. And a lot of them are educated in Faculty 73 or the auto universities. So VW plans to build up 10,000 and more software engineers. So the company is changing from manufacturing focused to software intense and software focused. And that is the case for many other OEMs too. Autonomous driving, every big OEM experiments with that. They work with startups to bring in the innovation here. VW does that with Argo.ai in collaboration with Ford, and those guys provide the self-driving system for VW. And to also vertically integrate the value add chain, they build gigafactories, batteries. Tesla is already doing that. They actually started with the cars and the gigafactories. VW is doing the same, and they are planning to be the largest battery provider for electric cars in the future. All this is connected to a platform, what they call a modular electrification construction kit, a platform where battery pack, motor, and all the constituents are packed, and you can have a modular design, and this is also sold to other OEMs. Now, let's have a bit look learning from the tech giants. So smartphone manufacturers, here an example, Apple. What they're good at, they know over-the-air updates of their software stack and new features to software. The platform ecosystem with value-added services is their strengths. The OEM can decide when a product would be obsolete. That's actually a dream. By deciding we won't provide a new software update for that particular hardware, they can actually sundown the system, and the customer is forced to buy the next generation. The design is modular for optimized mass production, and there's a huge vertical supply chain integration. Apple does their own chips, the M1 chip, for example, and they have a fully integrated supply chain. Let's look at what the OEMs in the automotive business learned from that. Now, they also look at new features, so software. Tesla has pioneered that. Sensors already in the car, new features can be updated to software. A platform ecosystem where the customer can log in and gets value-added services. Over-the-air updates to kind of update features and make the car more attractive around the life cycle. New business models, for example, for car data are coming up. And the rapid build up, what we saw in the slide also before, of electronics, ICT, and software competences. This is a completely new business for them. They're transferring in a major way. Let's look at the evolution of EE architecture. So what does it all mean when you look at the EE architecture? So the classic EE architecture of mid or premium cars was something where you had several ECUs, typically just for one particular function, connected to a CAN or LIN bus. You could have 100 ECUs, or some cars even had more and have more ECUs, embedded control units dedicated, they're interconnected, and they realize a hardware architecture for the car, for its electronics. That moved into something more sophisticated with different type of buses. The other buses were not fast enough, so CAN was augmented by MOST, FlexRay. The ECUs also integrated multiple functions so that you had software functions that were mapped to different ECUs, and one ECU could have really multiple functions. And a software stack was designed, AUTOSAR, Automotive Open Software Architecture, that allowed you to focus on the functions on the application software on a runtime environment that actually provided many services that didn't have to be rewritten. All the different bus systems were integrated through a gateway. But this architecture also was not sophisticated enough for the new generation. So the next step is looking at domain controllers. A domain could be chassis, domain could be ADAS, AV, domain could be infotainment. They were more powerful. They communicated with each other over high-speed connectivity. CAN bus moved to CAN FD. We got automotive Ethernet. So a technology actually that was known in ICT and network computers moves into the car. And now security issues came up. So that's why also intrusion detection systems could, for example, be integrated in the domain controller to make sure that intrusions could be detected in an early stage. But this is also not the last step. The last step goes into a high performance computing vehicle computing architecture. The need for that is driven mainly by autonomous driving and higher level of ADAS. So those systems are extremely powerful. Examples are the NVIDIA Orion processor, Xavier technology that has teraflops of computing power. There are different bus systems. Some are just for streaming data. There are vehicle operating systems, and the system is fully cloud integrated. And what it means is that certain functions are not running inside the car itself, but they're running in the cloud. They interact with the system. That allows for completely new distributed architectures. And you can imagine, suddenly, we have a whole bunch of classical ICT, cybersecurity or information security topics that are also relevant for the car because it's cloud integrated. Again, let's look at an example what that would mean. We look at the E-Class series, it's codenamed W21X. And what you see here is over the timeline, the number of ECUs, embedded control units for different models of this E-Class. Then you see the number of signals. A signal is defined as a measurement value that is, kind of exchanged on the bus. That can be a bus signal itself, or it can be a parameter measured. And you also see that's a yellow curve, the bandwidth need, which is actually skyrocketing because driven by infotainment solutions and autonomous driving solutions. Now you see, if you just mark one point here, in 2002, we had around 52 embedded control units and we had 5 buses. The number of signals was more than 4,000, but we are moving up to 9,000 signals, dedicated signals that are part of the signal matrix, canvas signals, but signals also in other bus architectures. And you see how the bandwidth needs are really driven up. So when we look into the latest architectures, like what's coming up in 2022, this is already moving towards vehicle computers, high performance architectures, and you see it's not the number of ECUs that becomes more, but now we have very powerful integrated high performance computers with high speed connectivity on par with the highest demanding desktop architectures or server clusters. This is a transformation towards ICT, and that has certain consequences from a cybersecurity perspective that I would like to look upon now. So the increased connectivity itself means we have a larger attack surface. If there's no connectivity, we can only physically assess a car. So USB ports, OBD ports, Bluetooth, and so forth. The increased connectivity means a very large attack surface. Self-driving and autonomous cars means that we have a severe impact of a cyber attack. We have higher risks. The car can be not only, kind of stopped, but the car could be turned into a weapon if an autonomous car is compromised. E-mobility, similar thing. We have higher impact of cyber attacks, possible spread of attacks to smart grid and smart city. We'll talk about that because e-mobility, electric cars might be also a part of a decentralized energy system in a smart grid that has bidirectional charging. When we look at shared mobility, what are the consequences there? There's a large attack surface also, and the entire fleet could be hacked. So it means not only one individual car, but maybe the complete fleet would be compromised. A very concerning point is the supply chain disruption and also the blurred borderline, the roles and responsibilities that we have blurred. Because that means there's increased threat of attacks in the supply chain itself, and when the roles are not very clear, or companies define a new role for them, but they are not very professional or very experienced in that role, which happens. Startups drive innovation, a good thing, but startups often work on short time to market budgets. So the products might have some security flaws when they go into other products. We know that from IoT startups. We know the press releases, nearly every day about some compromised systems that has to be avoided for the car. So one has to really look into that. And if you design systems with up to 500 million lines of code, you will make mistakes. There will be flaws. There will be design flaws. What that means is the increased chance of software vulnerabilities is there. We cannot avoid that. So we need very stringent processes, and we need to be aware of that there are vulnerabilities in the software stack. When we have high performance computing and taking all that together, software and high performance computing, the complexity that the industry deals with is just, humongous. That might lead also to design flaws. And actually, the teams are really dealing and they are struggling with this complexity. Now, what does car hacking mean? Well, one thing we can say is really all brands have been already hacked. So in no means taking 3 different, brands here would be any way, kind of blaming that brand for being hacked. Actually, in 2020, we had 200 officially reported cybersecurity incidents or car hacks. Out of that, half of that were black hats, the other one white hacks. So the black hats really with cyber criminal intention or hacking intention, the white hacks, for example, doing a penetration test or just looking at a proof of concept. So let's look at that. Nissan early on with the Leaf electric car now had an issue with the Nissan Connect app. Typical thing, there was only one vehicle identification number. With some issues, you had the chance to remotely control the car. For an electric car, if you switch on AC, the car battery will be drained on. If you log into the car, it's a security issue you have. A very prominent hack was the FCA, now today called Stellantis G-Pack. So the Jeep, the proof of concept by Miller and Balasek that showed that through the remote interaction with Uconnect, the infotainment telematic control unit, they were able to breach, 2 separate security domains, have a crossover and write on the critical CAN bus so that they could take over steering and the braking system. Now that is a very serious issue because a CAN is a signal and it's prioritized. So you have a big signal matrix in the car that normally is kept confidential from the manufacturer. And each signal has a priority and therefore identifies on the CAN bus. But if you know that, and if you can override it, and there are no other protection means, you can actually really remote control the car. And Tesla is a very special situation here because they have a bug bounty program. Tesla encourages hacking. They give you money if you are able to show a security breach. And so there were several vulnerabilities found in the infotainment solution and also some autopilot vulnerabilities, which is of course a sensitive area. Tesla, when you remember this, slide 4 architecture, a high performance computing vehicle computer has such an architecture where the infotainment and the autonomous driving autopilot domain is one hardware, high performance computer hardware that Tesla has designed themselves, and they have this vertical integration. They've done the chip design and have outsourced it. So it's done by TSMC or Samsung to produce the chip. Now, where are the entry points, the attack surface? We talk about a large attack surface that's created by the connectivity of the system. And here are some mentioned: the infotainment system and the telematic control unit, which is used for, vehicle to X communication. We have, of course, Bluetooth interfaces, Wi-Fi interfaces. There is an OBD port that is transforming. OBD stands for onboard diagnostic. Typically, this was where in the garage and workshop, you could override everything, diagnose the system, and even reflash embedded control units. This is now also taken into the cloud. We have new concepts of, diagnostics over IP. So we use Ethernet technology and IP technology for that, and also service-oriented onboard diagnostic that directly goes to the cloud for remote diagnostics. All these, systems that would have a direct interaction with the car and could direct kind of compromise the electronic architecture, of course, need to be very secure. Another point mentioned here is the supply chain, and that's a real big issue in the automotive industry because the disruption of supply chains, the different roles and responsibilities in startups leads to very complex supply chains. To give an example, an embedded control unit might have easily 12 different software suppliers, several dozen hardware suppliers, 1 or 2 first tiers that integrate the whole system, and you have to actually keep the whole supply chain, secure. How to do that? You need mechanisms to validate your software stacks. You need mechanisms to validate the supply chain. But it's new for the automotive industry, and it's a very severe topic that is also addressed by the regulation frameworks. Now let's look at the car in the ecosystem. When we get data out of the car, what do we actually want? What are the use cases and what are the repercussions of that? One is the car connected to the workshops and the manufacturing. The keyword here is Industry 4.0. So data is exchanged from the car. For example, we could have a process that automatically orders, part if it's compromised and has to be replaced. And this interchange of information is something that is possible now in this setup, this connected car data. Then we have the backend. The backend system consists of cloud-based servers where a lot of data is being gathered and analyzed for value-added services of the car. But also major security mechanisms are actually handled in the backend system. The backend system is a classical information technology backend. So it can be compromised by ransomware attacks. There can be privacy issues. And it is governed by classical information security. For electric cars, we have a connection to charging and batteries and the smart grid. And as I said, there's a trend towards more and more interaction, decentralized energy storage. In Japan, we already have this CHAdeMO, the system in place that allows bidirectional charging. Let's take, you have a PV system on your roof and some of this, electricity, which you don't need at the moment. You don't want to put it in the grid, but you want to put it into a car battery. How do you do that? And then after some time, the car battery would release that again, locally in your local grid. These are the visions of that, but actually the repercussions from a safety and security point are severe. And finally, we have the vehicle to infrastructure and vehicle to vehicle communication. That is necessary for any higher level of ADAS and autonomous driving, but also for many of the value added services. And you know, there are certain, kind of services that, brands, car manufacturers themselves have envisioned, like their own brand cars talk to each other, for example, to communicate free parking slots. Let's take a BMW or Mercedes would have these features. They tell the other cars of that same brand the parking lot on the roadside is free. They have measured it with their sensors, and this information is shared through vehicle to vehicle or vehicle to infrastructure communication. So there are lots of use cases, but the security is a big issue to authenticate and encrypt the messages that are being exchanged. Now, one of the research areas we're working on is to look at the cost of a cyber attack. Successful here means the hacker has been able to attack the company. What does it mean? And it's much more than just a monetary loss. Well, what are the components here? Vehicle recall and workshop costs. That's clear when, a cyber attack happens. But there's a high cost for fixing the problem under extreme time pressure. And as an example, again, the GPAC, where the Uconnect system was a vulnerability and it was not fixed in time. It actually was open for many months. And they had huge problems to actually update the software stack. That problem, caused huge cost and extreme pressure. Product liability lawsuits. Again, FCA had to pay a lot of money here to the authorities and to, individuals, because product liability lawsuits were pressed. The sale of the affected vehicle models might have to be stopped until the problem is solved. That's a worst case scenario, but it happens. The authorities could impose high penalties. Also, this is done. Several car manufacturers, especially in the US, had to pay these fees. There are copycat attacks. Once, a successful attack has happened, others will, try the same. So you have these copycats. The company itself could be perceived as an easy target. That would be really worse if they lose that. And the impact of connected and car IT service offerings, which you again see some companies have been hacked. They after that, try to kind of reduce the attack surface and reduce the services. They're just scared. Maybe they have a connected car data model, but they just stop it because they see it's too risky. We don't want to open up our cloud backend. We don't want to give APIs to consumers. The damage to the reputation is maybe the most severe damage of all. If does such a hack, is kind of going through the press and the people see the company is not acting on the cyber security threat, the reputation is damaged. Now, important, while we have a lot of security solutions to kind of, implement our security objectives and to avoid compromise of the hardware software architecture. The problem is not solved by, deploying a security solution. We need to have a management system in place that can actually coordinate all the different activities that are necessary. And it starts with a clear cybersecurity culture and a clear organization set up for doing that. So it goes into the organization itself, and clearly no role will be untouched in the engineering, production, sales, after sales process. Everything has to be taken into account. Now, when the cybersecurity organization has been set up, there's a continuous process going on to identify new threats, to analyze the risks, and to define the mitigation strategy for these risks. That's a cybersecurity program. This all has to be communicated inside the organization and also to the authorities and the outside, the suppliers. And finally, you will have to implement all your solutions to make the system, the car, more cyber secure. And constantly, this has to be monitored and audited. It's not a one-time effort. Like any software or any hardware or system engineering approach, if you want to be up to the level and the state of the art, it has to be running consistently, optimizing, consistently being aware of the threats outside and optimizing itself. This system is necessary. And when we look at the core activity of that, what has to be done time and again, it's this threat analysis and risk assessment. Let's quickly have a look at that. Let's say you look at the different assets in your car. You have to define the scope and clearly the boundaries, what's in, what's out of your analysis. Then you identify the assets which are threatened. It could be sensors, ECUs, different connected, interfaces inside the car, data assets, hardware and software assets. You set up your organization, your processes after you've done the scoping and your analysis. Then you go into this, which will be done many, many times, consequently orchestrated by the cybersecurity management system, the threat analysis and risk assessment. It's a systematic analysis of threats. You will classify, prioritize, and analyze threats. It's a risk assessment according to what you see as a risk or threat. You have to quantify the cost of the damage. And finally, based on that, you define your protection goals. You define the functional cybersecurity requirements to counteract the threat. And after that, you think about the technical implementation. How can actually be such a threat mitigated or avoided? That's a constant process. And you see, you will generate a lot of information while doing that. This is a similar process than you have for functional safety, which is called hazard analysis and risk assessment. And it's something that is constantly done. But there's a big difference to this HARA. Here in cybersecurity, your threat model, your threat environment is constantly changing. While in the functional safety domain, you have a one-time analysis of your hardware software, and you know what type of failures could happen. The cybersecurity domain, it's a moving target. Now, what are the things? We will look at the threats that could be, for example, spoofing, tampering, information disclosure, or denial of service. And on the solution side, we have the mechanisms to ensure confidentiality, to ensure integrity, to keep the privacy, and to make the systems available and keep the availability of the systems. When we do our risk assessment, it's always a kind of modeling of, how much, likelihood is there that, an attack happens. And the probability of an attack is a function of several things. System knowledge of the attackers, the budget, the motivation of the attacker. If they have an unlimited budget, a lot of things are possible. We know that in this critical infrastructure, for example, with Stuxnet, they definitely had a huge budget, but was then able with this system to attack, the enrichment facility in Natanz in Iran. We have to classify the damage and categorize it according to monetary loss, loss of reputation, privacy breaches, and loss of IP. And finally, the risk assessment is this kind of tuples, probability, and the damage cause, which gives us big matrices where we can then analyze each and every threat and see what risk it is concerned with. Based on that, we have to prioritize our cybersecurity measures because they also come with a cost. We see that later. So we need to prioritize and then decide and optimize what's the right cybersecurity mechanism for that risk and the threat connected to it. Now, let's look at the solution side. One approach, which is already well accepted in the automotive domain, and we are not starting from scratch here. When we look at the EE architecture in the modern car, it's actually already secured pretty well. We have different approaches. We have here a defense in depth approach, which is a standard approach to say we have to separate different layers like an onion model. And when we start in the lower part, now it's also already a standard to have complex ECUs with a hardware security module where you have your keys and your crypto algorithms. the crypto stack on top of that, secure boot and secure flash for starting the system is also already a standard in many cars. Then the network itself will be secured by encrypting and authentication of messages. Also that is in the next layer done. When we have external interfaces that have to be taken care of, and on the outer layers, we will have systems like firewalls. For example, you can imagine to the cloud backend. We might have systems of the intrusion detection that try to model the good behavior from the malicious behavior. And we will have security and secure communication built in. Now, that's inside the car, but the main problem today is all this connectivity to the car, and especially also the cloud backends, because these are classical IT systems and they are developed under enormous pressure. So there, what can happen is a ransomware attack on our cloud backend or on the automotive company as such that already, renders any cloud interaction obsolete, and the system, is completely connected. What do you do then? But let's look at the challenges. Now, security solutions are there, but what are some of the particular challenges? And that is something, I've seen myself, working on projects where cybersecurity requirements had to be integrated and where, the team struggled with that quite a bit. Now, with cybersecurity, a new set of security requirements must be managed and documented. And already we have a lot of requirements. Now, one example here is the in-car application server. It's a system architecture, which is, part of the modular platform of VW. But similar systems are used everywhere in this in the transition to high-performance computing and vehicle computer. It's a 4-core architecture, multi-core architecture, 3 different ICAS in the core architecture, and each one of that has about 10,000 requirements. Out of these 10,000 requirements, 1,000 requirements are security related, for example, for the different bus systems. That is an enormous number that has to be managed, that has to be taken care of. And unfortunately, often we have not a design, a security right from the beginning, but in a later stage, your requirements come on top and have to be met. The protection measures are computational intensive and drag performance from ECUs. We're not talking about IT security, where you have a lot, in the classical information security, a lot of computing power for intrusion detection, malware detection, and so forth. We are talking here about real-time systems designed, with a small footprint for hardware, software, and they, of course, need on top to run all the security algorithms. The biggest problem maybe at the moment is because we are still lacking all the standards necessary, that the systems are not interoperable, especially across different vendors. So now if you have different security mechanisms and have to make them talk with each other, take, for example, intrusion detection with a ECU protection mechanism and a bus encryption mechanism, then this might be an issue because there's not a standard that defines how those interfaces would be structured. False positives for intrusion detection devices would effectively create problems for the real-time behavior, and that happens all the time, while intrusion detection has not made it to a level how it would typically be, because it's a very useful mechanism to actually kind of mitigate cyber threats. And there's a license cost, and automotive electronics is always cost sensitive. The customer does not want to pay for cybersecurity explicitly. It must be kind of built in, and that license cost, who will bear them? So the security cost in the price sensitive segment is an issue. But there are solutions. As I said, the standards are very important, and some of the standards are like AutoSAF OpenC or security operating secure communication on board, and intrusion detection systems are now being standardized to be part of the automotive software open architecture. So then they're built in, they're transparently working, and they can be used by any OEM and first tier. Now the new regulations that are really helping. You know, some see them as a threat. There are so many regulations already automotive engineers have to deal with. Now new ones come called R155 and R56, one for cybersecurity management system, one for software updates over the air. And let's look a little bit at what these kind of new regulations demand and what are the consequences of that. So the vehicle manufacturer has to install a cybersecurity management system, what we saw before, and that has to be certified and proven. There's also a norm, the 21434, that gives, you know, a framework for cybersecurity engineering of the product. The cybersecurity management system covers the whole life cycle, so make it sure that the system is protected. The life cycle, the cyber attacks, the threats and vulnerabilities need to be monitored continuously so that, you know, the system can then also suggest the strategy to counteract cyber attacks. And when we look at that, this cybersecurity management system is applied to a particular vehicle type at the time of approval, and therefore it becomes relevant for the homologation and type approval. That's a new, because it means no car can be sold without a cybersecurity management system that has been certified and actually protects a particular vehicle edge type. And also the suppliers have to implement that. So it's not only the OEM who takes the burden of this to take it up. Risk management and constant tracking of efficiency and effectiveness of cybersecurity measures are necessary. So it's not a one-time exercise, it's a continuous exercise. The Automotive Security Operations Center is a needed system in place to orchestrate the threat analysis, then orchestrate any update has to be done to kind of counteract the vulnerability. And typically here, all the knowledge from, you know, intrusions, from threat intelligence is being integrated, and the orchestration of software updates happen to patch security flaws. That's done for the entire vehicle. The manufacturers will, as part of the R156 standard and norm, provide a software update management system. Now, some manufacturers already have that. Tesla has that already for a couple of years. That is necessary to patch a car, and when there's a cyber attack and some, you know, changes have to run on the software stack to act as soon as possible. Now let's look at it once again. It becomes necessary for type approval. What that does actually mean. The processes are being defined by the cybersecurity management, threat identification of risk, risk management, testing of the cybersecurity of your systems, the verification of that, all is orchestrated by the CSMS. The suppliers need to do that as well as the OEMs. Their over-the-air updates need to be in place, and the software identification needs to be traced so that you know what software stack is actually mapped to what car architecture. And this is then kind of applied to a particular vehicle type. How does it look in terms of the information flow? So we have different parties here. The OEM is a car manufacturer with a particular car, the technical inspection and service company, the TIC, and the authorities. Now, the CSMS certificate for a particular car will be kind of given to the technical inspection company together with the technical documentation. This is sent to the authority for validation. They look into the documentation and your CSMS. That actually then is kind of necessary for the homologation of a particular edge type. So a particular car that, you know, is kind of running the CSMS, and the CSMS is referring to this particular car. When everything is proper, the test report is sent to the authorities and they will issue the type approval. And this is done for every edge type of a particular car. CSMN, technical documentation, then the authority approves it. They look at all your documentation. When they find a flaw, it goes into an iteration. Otherwise, the type approval is given. And this has to also work if the software stack is changing, which is a very important part of that, considerations, because you therefore need identification systems for software. You need basically a bill of material for the software stack inside the car. Now, a quick look at the ISO norm. You see, it started from best practices from the SAE and in Japan and in Europe. And then the norm was designed to provide a guideline for the cybersecurity engineer of a car, what you should do. It doesn't give you a complete, kind of process, and not all best practices to do it, that the OEMs and tiers have to find out themselves. But it tells you what the goals and the objectives are and what has to be done from a process orientation. And it covers those fields here. There's a core of the cyber management, what we talked about, the cybersecurity management system, where the processes, the organizational parts of that, and the engineering outcomes and documentation takes place. It covers the life cycle, concept phase, product development, and operations. At the core is the risk management, the threat analysis and risk management, and it covers hardware as well as software levels. One way to validate and verify is a constant verification validation process of the cybersecurity of the systems along the integration chain. And you will have processes like in any systems engineering, kind of process within automotive domain. The supporting process help here. So that is the scope of that. This document is the framework, but the actual implementation and the best practices are things that the OEMs and suppliers work on and have to define for themselves. The Vehicle Operations Center will look at all the threat intelligence. What I said, in last year, we had about 200 incidents that were documented, but there are many more that are actually not reported and documented. If you look at production operation technology attacks, you will have thousands, sometimes a day, on all the plants of an automotive OEM globally. So here, as you saw in this picture about the connected vehicle ecosystem, we talk about everything. It's not only inside the car, but outside, and all connected systems are relevant for that. So what the system does, there's a central dashboard for all security relevant information, the mitigation and response mechanisms. Then you will have the security events to be gathered from vehicle network backend and IT systems. They have to be normalized. There is information from intrusion detection systems that comes in. And finally, with that, you do a threat intelligence. And we are working on something because here, other than in the information security domain, where you have standards for the SIEM and standards for threat modeling, CVEs and others, this is in an infancy still in this domain. How to define vulnerabilities, threats, how to classify them. So this is a lot what is done now as we speak at the OEM side or the tiers, and they define best practices and they need to standardize it, but we don't have that standardization yet. So what we are working on as a research domain is we build ontologies of threats and attack vectors. And with that, we make it accessible and we try to build up a common pool of threats. Some companies are already also doing similar things, but without the ontology approach, like Upstream Security in Israel. They provide an auto threat analysis where they have analyzed 600 plus security breaches and events that were reported over the last several years. But it should not be static, it must be dynamic, and it's a huge topic to come up with a good threat intelligence here. Now, as promised, we want to look at the final part of this talk on those two domains, battery electric vehicles and autonomous driving, and what actually could be attacks, and why are those attacks to these new systems different from what we have in combustion engine driven cars. Let's look at the attacks, typical attacks here for an electric car. You see, this is a platform with a battery pack, power electronics, axle and motors all integrated. On top of that, you would have your body in white, interiors, infotainment solutions, and so forth. And just a quick look at some of the potential attack areas. Well, attack on billing mechanisms for charging is something people seriously look into. Attack on the charging infrastructure itself, very important to be sure that this doesn't happen. And unfortunately, many of the charging stations do have loopholes where you can log in as a service technician, some even without a password, to set up from 100 amps of charging to 150 amps of charging current. So there are security breaches. The battery management system itself could be attacked. It's a very delicate structure. Thermal management is very important. And unfortunately, when the temperature rises, it's sometimes already too late because a process is initiated that, could actually burst the battery. So it's a very delicate thing. And imagine you would have a system similar to Stuxnet that actually compromises your thermal management or battery management, but actually all the higher levels in the EE architecture will get normal values, regular values saying not everything is okay. That's actually happened in the SCADA system there. So it was designed in such a way that it was very hard to detect. So this could really be a very scary thing if those battery management systems would be attacked. Of course, remote control features like what happened in the Nissan Leaf attack could be, kind of attacked. Switching on a system that is a load on the electric car architecture, and that would drain out the battery. For an electric car, would be really a very difficult case. The bidirectional charging has to be looked into detail. Actually, many are scared now. Bidirectional charging, what would it mean if this is not cyber secure and functional safe? What could happen? It's a good idea to actually create decentralized energy storage and virtual energy utilities, but it needs to be absolutely cyber secure. And then, of course, all the traditional attacks like unlock, theft of cars, and so forth are also possible. But the battery electric specific ones are very important. If you look at AV and autonomous driving, we have a similar situation. Lots of sensors, sensor fusion, perception elements, and planning structures. And there could be, and there already have been, attacks on the supply chain. You know that from the IT domain, SolarWinds, systems that were used in the monitoring and performance engineering of IT were compromised. And you could, how to prevent it when the systems themselves that at the core will be compromised. There could be attacks on the vehicle to infrastructure or vehicle to X communication. Attacks on smart sensors already have been reported. They could alter the parameters measured, and they could change them in very subtle ways. And do we know what type of software hardware integration happened there? Many of them are, sensors that are already built in, like for example in the Tesla, and later activated to software functions. The perception mechanisms themselves can be attacked. There are ways, for example, to attack directly a deep learning network algorithm in an autonomous car by, changing the ecosystem, by changing, measured values, and knowing the algorithms and knowing how to disturb them. This could be leading to very dangerous situations. And as we said, the cloud backend is very vulnerable because it's a classical IT backend. So attacks here could actually proliferate and spread in the, stack, and could have been devastating consequences. Yes, outlook and research areas to give you some ideas. Now, the focus here will be on interdisciplinary research on the edge of electronics, software, cloud computing, data science, and cybersecurity. EV cybersecurity is a lot more to say because it's a very complex system, as I said, up to 500 million lines of code. And the cybersecurity issue of such a system is a very important domain to increase acceptance levels, but also to avoid, big kind of cyber criminal attacks. The safety of the intended function for autonomous cars and ACS needs to be integrated. It should be a synchronized process of hazard analysis and cybersecurity analysis. The cost of cybersecurity has to be quantified because then we can offset the license fees and also the cost, the capex on cybersecurity solutions, and the companies will feel better because they have a clear understanding of the risk and implications. There are a lot of opportunities for machine learning and threat intelligence, but also orchestrating cyber analysis. And we see that in the intrusion detection, but also with building up security operations centers and also analyzing the different threats. Integrated approach, functional safety and cybersecurity. It's very important. A lot of companies are working that. Vector Informatik, for example, or Bosch ITES. That is a really big trend. It will have to be very well integrated. The vulnerabilities of battery electric vehicles. We have seen that they have a whole new class of vulnerabilities that have to be taken into account and have to be handled. And there's a automotive middleware, so the software stacks are very complex. This automotive middleware also has security issues and has to be analyzed. Some IP is, for example, one of those technologies that has been already analyzed in terms of its cybersecurity. And then the bigger picture. Automotive transportation is part of critical infrastructures. There we have smart grid, we have healthcare, the transportation, we have agriculture. So all this is also getting more and more interconnected in smart cities and smart, systems. So we have to look at that and have to also understand how cyber attacks could actually ripple through the system and how we could, on the system level itself, protect those subsystems properly. Cybersecurity for agriculture products is a huge upcoming area. You see tractors, autonomous harvesters, irrigation systems, and so forth. And typically there's a lot of lessons learned from the automotive space to there, but on the other hand, from that space also to automotive, because large systems and agri-tech products are already autonomous. They're already very well connected. So in both sides, there are interesting learnings. Finally, vehicle to infrastructure cybersecurity is a very important domain because we will see more and more systems that communicate with a car, like a signal or a traffic sign or other roadside systems. This has to be secured, authenticated and secured. And finally, the ransomware attacks on automotive IT is an upcoming domain. You are well aware about WannaCry, Petya, and so forth. These systems can actually compromise backend systems, and these attacks can render the whole cloud and connectivity infrastructure completely sundown it. That is a very critical issue. In summary, we looked at megatrends. Vehicle fleets can be a target for hackers, and they are being hacked. Cybersecurity in the automotive space requires a holistic defense and depth approach and across the life cycle. The standards that are emerging help the engineers to understand what are the objectives and what are the processes, but the best practices they have to develop themselves. The cybersecurity management system at the core helps to orchestrate those things, provide the life cycle reach, and it helps to orchestrate the work share between OEMs and suppliers in securing the overall system. VPR155 is now coming, is already there, but as from next year onward, in July 2020, every new car has to comply with that, and it's necessary for type approval. It's a good thing because it gives more clarity of what has to be done to secure the car. And one of the large areas where a lot of research is to be done in the future is the Automotive Cyber Security Operations Center that monitor the threats and integrate all the measures for the fleet. That has to be standardized, and we need more and intelligent mechanisms to integrate all the information sources that are available, and then provide the right strategy to securely update the fleet across the globe. With that, and a few references here for my talk, I would like to, close the talk itself and, lead over to the discussion.
Yeah, thank you, Professor Haas. That was a very interesting talk. So there are already 2 questions in the chat window. So the first is by Dr. Milind Gandhe. Dr. Gande, you want to unmute yourself and ask the question yourself, or should I read it out for you?
Professor Haas, just a quick one. So two things actually I wanted. One question that I had listed was, there is a public domain list called OWASP, which highlights the top 10 security threats to cloud applications. And I think they have an embedded variant as well, or they're working on one. So is there such a similar list of the top 10 cybersecurity threats for automotive? And second, could you speak a little bit more? I know you alluded to Tara versus Hara, but could you speak a little bit more about the comparison with let's say functional safety standards such as 26262 and the standards that you were alluding to for cybersecurity?
Yeah, sure. So coming to first question regarding your threat intelligence and databases that talk about threats and kind of classify them, that is coming up right now. And there are certain initiatives from private companies like Upstream that provide such a database on a subscription model. So their idea is really to provide all reported cases, classify them, structure them, and then disseminate this information. But it's a subscription model, it's not freely available. On the other hand, there are a kind of associations that talk and share that knowledge, like the IIITB, that was created primarily for this, to share threat incidents and best practices and talk about that in an open way. However, the IIITB always suffered from one thing, that the OEM suppliers and the supply chain didn't want to speak openly often. So they were, kind of not like in the classical IT cybersecurity space. There was kind of constraints by their companies or by the incidents, what they could report and what they were not able to report. And of course, that doesn't, it's not so helpful if those cases cannot be, reported very openly. So it's coming up, but it's still an issue. We need to see more that this threat intelligence is made available to everybody and accessible. The second question regarding Hara and Tara is a very interesting one. I think one of the major differences is really that, the cyber Tara is a very dynamic process. It has to be done constantly because the threat environment is changing. And we have new attack vectors that might have not been relevant half a year before. There are new agents and new attackers coming up, and there are new ways and vulnerabilities being reported. The idea is that at a certain point of time, we will have a very integrated process. Some, kind of best practices already showing up. For example, Vector Informatik is doing quite a bit on that. Integrating the functional safety analysis like the 26262 process with the cybersecurity engineering process. It's the ISO 21434, so that you have an integrated process. You can go across the V model, and then while you do the analysis on the functional safety side, you also integrate the analysis on the cybersecurity side. However, this is a process which is, still, something that needs more research, more best practices, and it also needs feedback from the industry, how practical those different approaches are. But it's being done, and I think it's also a very fruitful domain for research and activities, the integrated functional safety and cybersecurity approach, and extending that to the safety of the intended function and cybersecurity approach.
Yeah. Thanks for the answer and the question. Professor Srinath has a question. Professor Srinath, ask it yourself. Okay, maybe I can just read out his question. Some years ago, there was a lot of interest in automobile to automobile and automobile to infrastructure communication. How is this field of work faring now?
Yeah, that's a very important question, because actually there were a lot of hopes and promises in this domain, connected car data, sharing connected car data, and kind of new business models emerging out of that. What we see is on the commercial consumer side, with car data and connected car and kind of use cases, there we have a little bit of, downfall of this big enthusiasm which was there in the early years, because the revenue being made through these telematic services was lagging far behind of the estimations and what was promised from the industry. And we see that also time and again when car data projects, kind of strip down, and OEMs also decide to discontinue certain services. But on the other hand, what is really emerging is when we look at ADAS and autonomous driving, that's a must. You need to have this connectivity and this communication to infrastructure, to backend, and to other cars. And when we see more of ADAS and autonomous driving cases, and some are even, cases like automated valet parking, where the car is guided into the parking house, parking structure automatically and communicates with the infrastructure. There are many very useful cases how that can be done. And those cases, I think, will drive also in the future. Again, an enthusiasm in this vehicle-to-X kind of domain. Finally, with a battery electric vehicle, we will also have more need for that. Communication to charging, communication to backends. There are many new models, for example, even the monitoring of the battery system in the cloud. New services that are coming up. So I see there will be maybe a revival of vehicle-to-X communication through the battery electric vehicle.
Okay, great. I have a question myself. I want to draw a comparison to autonomous flights. Okay, I want to draw a comparison between autonomous cars and autonomous flights. So if I'm not wrong, even the current commercial flights are autonomous. Okay, so my first question is, okay, why it's easier to design an autonomous flight than an autonomous car? And then second question, why aren't the threats on cyber attacks on the flights not as prominent, or it's not as much discussed as attacks on autonomous cars?
Yeah, very good. Maybe I start again with the first question you raised. The difference is really the dimension, the car within the structure, unstructured environment with a lot of different obstacles coming up on the road, versus an aircraft that is in the third dimension flying. There are the obstacles, of course, other aircrafts and so forth, but it seems like that the autonomous flight path there is relatively simpler than what all has to be considered for the autonomous cars. And one of the issues autonomous cars will face is that it's not every car is autonomous and they can automatically communicate with each other. For many years to come, you will have autonomous cars and cars that are driven by a driver. So that creates a heterogeneous environment which is extremely complex to handle. And maybe one of the major problems for autonomous cars is that because the humans behave in a different way, and some of the major accidents for example, Google Waymo cars is a human driver crashing into the back end of the Google Waymo, because the Waymo sticks to traffic rules. The human drivers is a little bit more flexible regarding that. The other question is also very, very relevant. I think one of the important aspects is that flight software, software in the aircraft, exactly everything connected to the flight control, is extremely stringent in the development process. And you will have much, much less code than we see now, right, going into a car, so that you can verify the code. The cyber threats that could come to the aircraft might be through, infotainment systems and so forth, might be also through updates or sensors and the supply chain. And there definitely also are some there, but you're absolutely right, they are not so prominently being reported. And I guess there is a little bit of fear in the industry also that people could hack into that. You have those cases that some hackers are not let on the flight because they have reported how they would hack into the infotainment system just before. That happens often on the DEFCON conference, that people cannot come because the airlines would not transport them. They're just scared about it. But I guess the issue is also important, and the infotainment systems, sensor systems, and supply chain could be a big cyber threat in the aircraft business.
Thanks. Are there any questions, please? Okay, so if there aren't any more, so then let's thank Professor Haas for a wonderful lecture. Thank you, Professor Haas.
Thank you very much. It's a pleasure. It's a pleasure. Stay safe and secure.
Thank you, Professor Vivek. On behalf of Team Samvaad, I would like to thank our speaker for today, Professor Haas, for an extremely exciting talk on such a cutting-edge topic. I would also like to thank Professor Vivek to take his time off his schedule and be able to chair this session. So on behalf of Team Samvaad, with this, we come to the end of the cybersecurity theme of talks. And with the next theme on a roadmap to 5G and beyond communication starting next week on Monday, we have an exciting lineup of talks. So looking forward to much more interactions from all faculties and colleagues and students. Thank you so much. Have a nice day, everyone.